How's it going, everybody? And in this video, we're going to be walking through the thermodynamics of a Wort chiller. This is also called an immersion heat exchanger, and we are using them in practice in benchtop scale beer production. And the reason why we care about Wort chillers is that as we're brewing beer, one of the first steps is basically creating a sugar water solution before you pitch your yeast into it. And as you are doing that process, that sugar water is at 100 degrees Celsius boiling. And so if you were to pitch your yeast at that point, you would kill all your yeast and you wouldn't have any beer at the end of the day. So what you need to do is you need to chill your wort down to a more reasonable temperature around 20 degrees Celsius, which is about 70 degrees Fahrenheit, as quickly as you reasonably can. And the reason you want to be quick in this step is because the longer your sugar water is just exposed to other things out there like bacteria or other kinds of microorganisms in the air, the more risk of contamination you have. So ideally, you chill your wort as quickly as you can, you pitch your yeast, you cap it, and then you are able to ferment that sugar water with the yeast now that they've got a bunch of food to play with. And so that's the whole reason why we care about wort chillers, is that they help us chill that thing down so that our yeast can actually live in there and be happy and thrive. And so there's a ton of thermodynamics and fluid mechanics at play here, which is the reason why, to me, this is personally a very interesting and exciting subject. This end right here screws onto a hose, and you basically run water through this thing, or at least that's what we're doing at our little benchtop scale. And then it's going to flow through all these copper pipes, and because copper is great at conducting heat, that boiling water that's surrounding in here is going to be transferring its thermal energy into the copper pipes. And as our tap water comes in, and we'll call that some fixed number, we'll call it like 60 degrees Fahrenheit, that tap water is going to come in and it's going to heat up as it flows through all these copper pipes, and it is going to eventually exit our system, our immersion heat exchanger right here, out of our wort with all that thermal energy. And as it does that, it's cooling that thing down much more quickly than it otherwise would. Another thing I'm going to make note of is the tuning parameters at our disposal before we jump too deep into math, is just thinking about the properties of the fluids involved here. So, you know, we use tap water, but sometimes you'll see, especially with the more higher production volume people with beer, they're going to use other stuff, other coolants like glycols, and that's because they've got better heat transfer coefficients. So they're going to absorb even more thermal energy as they flow through our system. They might also be less corrosive to all these copper pipes, you know, especially if you're doing this with hundreds of gallons of beer, you know, all year round. And then other properties at our disposal are, you know, material choices. Sometimes you'll see these things made out of other materials like nickels, and get really fancy and do countercurrent heat exchangers, which gets super expensive. But for the purposes of just, you know, a basic benchtop scale homebrew setup, this is about as good as it gets given the cost. You know, I bought this thing off Craigslist for about 20 bucks. You can buy them new on Amazon for 60. The material alone is, you know, the copper is a bit expensive. So, but, you know, you do what you can. This really speeds up your fermenting process and results in better quality product because you're not running that risk of contamination. So as an insurance policy, I would argue that this thing's almost worth it. And so now we'll jump down into the weeds and figure out how we can get a model and a graph that shows us how quickly or how long we'll need to wait to actually get our wort chilled to the correct temperature, as well as, you know, what other tuning parameters can we change here to maybe speed up that process. So stay tuned. All right, and before we dive too deep into all the math, what I have here is a Python script that I wrote that essentially takes all of our parameters in our model, and then it will evaluate the temperature of the wort at a given time. And so basically you can come in here and you can change this. I'm going to make this a public GitHub repo, so anyone who wants to can come in and try what happens if you use a different material property that alters your overall heat transfer coefficient, for instance, or if you changed your coolant flow rate, how would that impact the overall time it would take for you to get to a given yeast pitch temperature, and stuff like that. So I'm just going to walk through this real quick. But before I do that, I will just run this thing so you guys can see what it does. And so I have it use the Matplotlib package in Python, and it basically tells us, you know, an approximation as to, you know, given these particular initial conditions, like our starting temperature of our wort was at 100 degrees Celsius, and with that, it's going to take us for a 3-gallon batch about 610 seconds. So that's about 10 minutes with our immersion heat exchanger to do this operation. And so I'm going to close this and we'll walk through what's actually going on here. So basically, we're going to do a deeper dive of this in our model, but the first thing is the constants. So we're basically saying, what is the diameter of our heat exchanger pipe, and then what length of this heat exchanger pipe is submerged. I want to make note that we have to be really careful with dimensions here, because if you use the wrong dimensions, it will throw off your measurements by orders of magnitude potentially. So be really, really careful, exactly what dimensions we're working with here. And then we're also using that to essentially calculate what is the outer area, the surface area of the heat exchanger that's exposed to our actual wort. And then also U naught right here, this is a big term that is our overall heat transfer coefficient. And this is something that depends on the heat transfer coefficients of the fluids, as well as the type of material that we're using. And so this in and of itself can be an entire script or function basically that you would be needing to calculate and determine. So empirically, you would have to on your own calculate these values. 1500 is the ballpark, and 1500 is what we observed when I ran this in past lives. So that's what I'm going with. And the units here are watts per meter squared per degree Celsius or per degree Kelvin. They both have the exact same dimensions, or their equivalent dimensions. And so basically we've got all that stuff defined. We define what our density of our coolant is in kilograms per cubic meter. We define the flow rate of our coolant in liters per minute, which is about 4, so that's 1 gallon or a little over a gallon per minute. And then I convert this to cubic meters per second to make sure that our dimensions are agreeing with each other. We've also got our specific heat capacity of our fluid, of the coolant fluid. So in our case, I'm going to assume it's water because that's what we used, and I'm going to assume that it's basically going to be 4,184 joules per kilogram per degree Kelvin. And then we're using that to calculate that K constant. It's basically a dimensionless quantity that appears in our calculations. And this is something that we'll look more into in our model. And then I also set the constants here. We have that inlet temperature of assumed to be 15 degrees Celsius at all times. And then I'm also having the initial temperature of our wort TH naught be 100, so that's that 100 degrees Celsius boiling point. And then we've got some wort parameters in here. And so these guys are as follows. I'm going to assume that basically the density of the fluid of our wort, that actual sugar water itself, is still about 1,000, but as we know with specific gravity, it does change slightly as you dissolve more and more sugar into water. That does change it a little bit. So those are things that you can calculate on your own, and I would recommend you do if you want to have a more accurate model. And then I also have the number of gallons of wort. So in our case, we have 3. And so this is the total number of the volume, and then I convert this to cubic meters, again, because we need to make sure that our dimensions are going to agree correctly for all of our math. And then we've also got the specific heat capacity of our particular wort. Again, I'm assuming that our wort is going to have the same specific heat capacity as water, 4,184, but obviously in practice, this is something that you would make use of like a bomb colorimeter for, and just empirically calculate this for yourself to make sure that your model is as accurate as you reasonably can get. So that's an assumption. And then also in terms of the time dimensions, I'm going in seconds right now because that is standard metric units for time. So just make note of that. And basically what I'm doing, because I'm not really using NumPy, which may or may not be foolish, but I'm just literally making a list from 0 to 1,000 in increments of 10. And basically that's just every 10 seconds it's going to redo the calculation of what our wort temperature is at that time with all these parameters that we've just defined. And so basically it's going to go through, calculate that, and then we also in our model are able to calculate the exit coolant temperature from the wort temp. So with that, we'll also be looking at that and getting those values. And then finally, I did add a little method right here that basically looks through the wort temps to find exactly when is the time that which you should pitch your yeast, assuming some specific yeast pitch temperature. And in my case, I'm assuming that's 25 degrees Celsius. If you had a different strain of yeast, maybe they would want to have a even lower or higher pitch temperature. So obviously this all depends, but it just prints out for us in a little annotation on our plot when to do that. And then these are all just functions associated with actually plotting our method like that. So I'm going to run this one more time, and we're just going to make note that basically with everything we have here, it's going to be about 610 seconds before we are able to pitch our yeast. if we have our flow rate set to 4 gallons per minute, or I'm sorry, 4 liters per minute, which is about that 1 gallon per minute thing. So maybe you ask the question, let's see if I double that, how much better are we going to do? It's pretty cool. You can just update that just like so. We're going to stop this thing, and we're going to then rerun it, and we will expect to see a slightly lower pitch time, and we do. So we're seeing how this plots the volume, which is pretty cool. And obviously there's going to be a law of diminishing returns here, but we just doubled it. So now we're using basically 2 gallons per minute of water. And then if we want to get crazy, let's do like 10 gallons of water per minute, which would be 40 liters per minute. So basically I'm going to stop that and run it one more time. We're going to see how we're hitting this kind of diminishing returns pretty quickly. So even though we're adding a ridiculous amount more water or pumping it through our system, it's not actually helping reduce the pitch time that much. So that's the reason why this model is so cool, is that you can just run this stuff just like that. I'm going to take this back to 4, which was our original value. And then another thing I want to look at that we can change would be something like our overall heat transfer coefficient. So, in our case, we were using a pretty easy, that immersion heat exchanger, and basically that fluid goes in and it gets its one-time pass, and then it leaves our system. And it's okay. It's not the greatest, but let's say we wanted to use more exotic materials and go with some kind of countercurrent heat exchanger. When you start making those types of changes, you can start getting an overall heat transfer coefficient that would be even better. So let's say, and basically, when you go to buy your immersion heat exchangers from the store, the manufacturer or supplier should be telling you, hopefully some information would help you get to this value. But you can see, like, again, where is your money best spent here if you want to scale up some process. So if instead of 1500, let's try 3000 and see if that actually helps. And just remember that 610 was our benchmark from that 1500 note. So I just doubled our overall heat transfer coefficient, and then I will run this guy, and we're going to see that that had a huge impact as well. So, if we're able to figure out ways to change the flow regimes or change the materials such that, we can double our overall heat transfer coefficient, we're minimizing that resistance to heat transfer in our system. And again, another great way of reducing the time it takes to actually cool our system down. So that is going to wrap things up for the model. We'll now dive deep into the math associated with this stuff. So you guys can see all that if you care about the theory of all this stuff. But for sake of just a simple model to start playing around with and try different scenarios, this should get you started. So I hope this helps, and stay tuned. So basically what we have here is a little diagram on the left that's showing us that copper tubes that we were looking at. That's these red lines in the swirls. And then we've got our submerged immersion heat exchanger in our Wort, and this Wort has a mass m sub h and some temperature T sub h. And then the other important things to note here are that basically we've got the inlet coolant temperature, TCI right here, and we've got an exit coolant temperature, TCE. And so basically what's happening again is that as your coolant is flowing through these copper pipes down and through all those swirls, it's taking away that thermal energy from our Wort, which is actually cooling it down. So basically over time what's happening is we're going to expect our Wort temperature T sub h to decrease, and we would also expect the exiting coolant temperature to also be decreasing and approaching what our coolant inlet temperature is, and this will be assumed constant like that. So these are the models, and then also from our little measurements, we found that the outer diameter was equivalent to 9 millimeters for that copper pipe, and then the inner diameter was 6 millimeters. And then the length, this L term right here, is basically referring to the length of the stuff that's beneath our water. So all this guy right here would be valid, but not the stuff above it, because that's not involved with the actual surface area contacting the Wort itself. So that's what L is really referring to. We're going to actually start looking at some equations here. So basically, we have rho sub h times v h, and this is just mh. So that's the mass of your Wort times the volume of your Wort. I apologize, my thing's crazy right now. So this is just the mass, and then this right here is your specific heat capacity. So basically, specific heat capacity intuitively is telling us how many joules of energy are needed to raise the mass by a given degree. And then this dTh by dt term is telling us how much temperature has changed over a given time interval. So this is equivalent to energy per time when you do the dimensional analysis on this guy. So this term on our left is telling us basically the energy lost by the wort, and the wort again is all the fluid inside of this, and I'll try to use colors that are appropriate. So the wort is all the stuff inside here. And so the energy lost by our wort is going to be equivalent to this term on the right, and this guy is going to be the energy absorbed by the immersion heat exchanger, which we also are referring to as our Wort chiller. And so this is the IHX for short. And so basically in this term, what we have here is this minus U naught. This is called our overall heat transfer coefficient. This A naught term right here is equivalent to all that surface area that we have available for heat transfer to occur. And we've defined it right here to be that outer diameter times that length of the submerged area times pi. And we've also got this other factor, the delta T LMs. This is the log mean temperature difference. The reason why we need to use delta T log mean is the fact that as your coolant is flowing through these pipes, it is increasing in temperature, so the temperature differential will actually be a function of where you are along that pipe inside, because the temperature right here is going to be different than the temperature right here. It's going to be different from the temperature right here, right? So basically, how do you figure out an aggregate of the temperature differential along this whole thing to figure out how much driving force do you have for that heat transfer to occur? And so the way you do that is through this delta T LM term. And something I want to make note of here is that when we're working with this stuff, this is a function of time. So this is time dependent because over time we're going to expect our wort to be cooling down. We're also going to be expecting our coolant exiting temperature to be cooling down along with it. So make note that this TH term, this is your wort temperature. And this is the thing that we need to make sure gets below 70 degrees Fahrenheit or 20, 25 degrees Celsius. So this thing is going to be changing over time. And then we're also going to be expecting our wort, our coolant exit temp to also be decreasing along with it as we're going to have less of a driving force between it. So basically these terms are very time dependent. But we do have the TC inlet here, this guy, inlet coolant temp, and we can assume this to be constant for our purposes because we'll just assume that during our whole wort chilling process that our actual tap water is the same temperature throughout, and we can call it something like 60 degrees Fahrenheit or whatever. So, but basically that's a key parameter in this equation, and at the high level, even if you don't get any of the math, the whole point is that all the energy, we are assuming that all the energy lost by our wort is being absorbed by our heat exchanger right here. In reality, the situation is that we also have an additional heat loss, which is actually kind of helpful for us, exiting from the conductive heat away from like the metal pot. So when you're boiling this wort in that metal pot, it's going to heat up the sides, and then you're going to have some losses out through here. But if you have done this before, you'll know that this Q loss term is actually pretty small, and that's the reason why if you didn't have a wort chiller, aka an immersion heat exchanger, this whole thing is going to end up taking you many, many hours to actually chill down. So that's the whole reason why we're using this wort chill in the first place, is that we are trying to do this much more quickly. So this Q loss term in our calculations, we're assuming that to basically be negligible, just so we can focus on modeling this and have some more reasonable approximations. So that's our log mean temperature difference, and that's how we're going to model or describe the energy absorbed by the immersion heat exchanger, which is the wort chiller. And so this is basically just some math. Now what we're going to do though is we're going to make note that this term right here again is the energy absorbed by the immersion heat exchanger is going to basically be equivalent to energy absorbed by the coolant. And so your coolant is going to have a flow rate. So if we're using tap water as our coolant, the density of water that's going to be 1,000 kilograms per cubic meter. And then this Q term right here, this QC is the flow rate of water. And so if you're using tap water, a typical flow rate would be like 1 gallon per minute. And I'm going to approximate this as 4 liters per minute. And then this right here is your CPC. This is your heat capacity of your coolant. And for water, that's 4.18 joules per, or kilojoules per kilogram per degree Celsius. So it basically takes 4.18 kilojoules to raise 1 kilogram of water by 1 degree Celsius. That's how much energy that water is taking with it out of our system through that heat exchanger. And then finally, this TCE minus TCI, that's our exiting coolant temperature minus our inlet coolant temperature. So that's, this term on the right is really telling us what's going on, where's that energy going, and it's going into heating up our coolant in our system. Okay, and so basically, key thing to make note of here is that we can now do some more rearranging to get this into a state where we can actually arrive at a time equation and solve a differential equation for that first order. So basically, this right here, your exiting coolant temperature sensors, exit coolant temp is going to be dependent on your Wort temperature. And this is the thing that the whole reason why we're doing this in the first place. We're trying to chill this whole thing down. And this is going to be equivalent to these terms. Again, this is just rearranging the terms in these equations that we've been walking through with our energy balances. And so basically, this guy is equivalent to TH again minus TCI. That's your inlet temp. And then you've got this exponential right here. And in this exponential term, we're seeing again that A naught term. And then we're also seeing this U naught term, and this is your overall heat transfer coefficient. And this term is where people spend lots and lots of money on exotic materials and exotic fluids. And so, the whole reason why we care about this stuff is that basically this overall heat transfer coefficient is telling us, how is our system resisting heat transfer? Like if we had a terrible heat transfer coefficient, basically our immersion heat exchanger wouldn't be doing anything. It's not taking any energy out of our system, so the temperature's not going to cool down any faster, and we're going to defeat the whole purpose of this thing. So ideally, you spend money on the right materials and figuring out what are the right flow profiles to have. And so it's a very important term in this equation, and it is a constant term, assuming that you're going to keep your flow rates constant, your materials are not going to change throughout this process. You're not taking into account anything like corrosion or stuff like that. So it is a constant. I just want to call that out too. And then the other term we're seeing right here, I'll use red, is basically us calling out our coolant flow rate. And this is so rho C QC here. That's the coolant mass flow rate. And the whole reason why it's in this term is hopefully it makes intuitive sense. As we increase the amount of coolant flowing through our system, we are going to be able to extract more energy, but we're going to do so at a diminishing rate of return. So with this, basically, we can flow a lot more coolant in, but what we're going to note is that we've got this term in our denominator. So basically, the more coolant that we continue to flow, it's going to become smaller and smaller returns basically on our investment. So coolant gets more expensive the more you waste, because in our case, we're just dumping our heated up coolant down the drain. But even if you recycled it, there is a cost of having higher flow rates, and that comes in the form of having bigger pumps. So again, it really comes down to doing a cost-benefit analysis here in terms of like what coolant flow rate are you okay with versus how quickly do you need this thing to cool down. And the argument there is also you need to worry about how much risk are you okay taking on this batch to have your process have more contamination potentially, because the longer that thing's cooling down, the more opportunities there are for stuff other than yeast to get into it. And then also how quickly do you want to be churning out your beer? Because if you're okay having a lower production volume, then you can have a slightly slower process too. So it's like you're going to get less product because your process is slower, but you're going to, if you wanted to speed it up, you do it at the cost of more coolant flow rate. So another design consideration, as well as pump operating costs and capex to buy those pumps. So basically, we're seeing right here how economics is coming into this picture, and that's the reason why I love this. I think it's great But basically what we're doing is we're lumping this entire term, this whole exponential, into this term right here, k. And that's because k is just a constant. It is a constant that we have the ability to change through different materials or different flow rates. But during this whole process, we're going to assume that those are all the same. So k is going to be the same here. And so now what we eventually arrive at is this is an equation. Again, all these TH terms are stuff that depends on time, as well as our coolant exit temperature. And so finally what we can do is we can rearrange stuff and then do an integral. And basically this is integral from 0 to t, and we're making the assumption that your wort is going to have some initial condition. It's going to have some initial temperature, TH naught. This, we'll assume that's 100 degrees Celsius. Basically, we're going to assume that, at the start of our model, our wort is boiling. And now we're seeing where time comes into this picture. And we're also now having TH as a function of only constants in time, which is great. So again, just kind of spelling this stuff out. TCI, that's your inlet temp of your coolant. And then that's your fixed number, the initial quantity. And again, we're seeing how our coolant flow rate's impacting this. We're also seeing how the mass of our wort impacts this. So basically, if you had an enormous wort, it's going to take even more time to cool it down than if you had a small, tiny wort, because there's just less mass to cool down. We're also seeing how coolant flow rate's impacting this. So, if we increase our coolant flow rate, we're going to expect our time to not be as much for achieving the same amount of cooling power. So again, hopefully these equations make intuitive sense. These are the specific heat capacities for these guys. So, if you talk to more professional brewers that are doing stuff at higher scales, we can see how if you turn to exotic coolants that have different specific heat capacities, you can get these numbers to be higher. So that basically means they're going to pull even more thermal energy out per kilogram of coolant that goes in there than with water. So people turn to glycols and other types of stuff. Obviously more environmentally impactful, but at the end of the day, you can have lower flow rate pumps, save on the electricity you need to run those pumps, and then also the heat capacity of your actual solution, which in our case is our wort, also is making a big impact here. So basically, if you had we're going to assume that our beer is basically like water, or our wort is basically like water, but depending on the types of hops you've added or the types of sugars you're using, maybe your specific heat capacity can take on different characteristics, and these are things that if you wanted to have a more accurate model, you would have to take into account. And then we're also seeing where this K term that we talked about earlier is coming into this whole exponential, which involves that overall heat transfer coefficient, again, is showing its face in here. And that overall heat transfer coefficient is where we're factoring in stuff having to do with the material properties and the flow profiles that are going on in our actual system. So this is the math that's involved here. And basically, this is the thing that at the end of the day, we can make a plot of. And I'm going to do this in Python, but basically, just intuitively, what do we expect to have happen? So we've got time right here. We're going to have the temperature of our worts right here, and obviously we're going to have an initial condition. We're saying that that's t equals 0. We're going to have some that th naught, which was equal to 100 degrees Celsius, right up there. And then a final thing, or something I want to call out too, is that basically if we plot this, we also are going to expect that over time, the best we can possibly cool our overall wort to is going to be bounded by our inlet coolant temperature. So you're never going to chill this thing below this coolant temperature. It's going to get very, very close, but it's never going to actually reach it. And so again, that's just another cost-benefit analysis thing of how long you're willing to operate this process to get as close to TCI as you can. And then the final design consideration here is that, for the particular type of yeast that you're using, yeast must be pitched at 70 degrees Fahrenheit or something like that, or whatever, but just there's going to be some temperature that the yeast need to be at. So basically, the whole point is that your TCI obviously needs to be lower than this demanded temperature. So hopefully your coolant inlet temperature is around 60, and then the time at which you could actually pitch your yeast would be right here. just like that. So that's the whole point of this model, is that it can give us a plot like this, and then we can also try changing properties, see how much it's worth to us to be able to, you know, try a different coolant with a different specific heat capacity, or to try different materials, like, you know, maybe there's something better at heat conducting than copper. That would update our overall heat transfer coefficient in this K term. We can try a different design that has more tubes with more area. So again, very, very important stuff to be taken into account. And then also, this bottom equation right here is showing us, you know, this is that overall heat transfer coefficient and how we can calculate it. So H sub O, H sub I, these are heat transfer coefficients of the fluids themselves, and these are things that you need to experimentally determine. And then this right here is the basically the resistance to heat transfer that is caused by the copper pipe itself. So it's drawing an analogy here. It's like we have three resistors in series to our heat transfer. This guy right here is referring to the copper thermal conductivity. That's what this K term really is. So if you got gold, you know, if you really wanted to go all out, gold would have an even better K term. Obviously, it's going to cost more money. And then you've also got this length term. So the more length of tubing we have, or the different diameters we go with, we can change the amount of resistance that there is to heat transfer. Obviously, we want to make the resistance to heat transfer as low as we can to facilitate cooling this thing down as quickly as possible. And then these guys right here have to do with the heat transfer coefficient for the fluids. So this H sub O term is referring to your actual, you know, your wort itself. So, and then same thing for this. This is going to have to do with your coolant. And again, fluid mechanics coming into this picture. It's very important because basically, this is, depending on your flow regime, you can have bubbles present that would really impact this, because obviously air is very poor at heat conducting. So making sure that you understand the flow profiles are also important. But for sake of modeling this stuff, we're going to see where our volumetric flow rates come into this picture. And I'm going to go with a number that we've experimentally evaluated when I was at Berkeley. And in our specific setup, our heat transfer coefficient was equivalent to 1500 watts per meter squared per Kelvin. So that's what I'm going to be using in my design equation, or in my model. But obviously this is stuff that if you're ever going to get super serious about this and want to model it yourself, you're going to have to manually calculate these terms just through experimenting and plotting those temperatures, and also just looking up the properties of copper. So, and making those measurements, knowing what your internal and external diameters are. So this right here is all the theory that we're going to be using in our model. Again, key things to call out here, if you're still with me, is that, you know, we are making a bunch of assumptions. We're assuming that there's no heat lost. I also want to make note that we're assuming that the specific heat capacities of the actual wort itself and of the coolant are not functions of temperature. In reality, the specific heat capacity of the fluid does change slightly, or does change based on what temperature we're at. So if you want to get even fancier and even more math to make this crazier, you can absolutely do that. We're also not taking into account the fact that, you know, potentially there is a reaction going on in here, and so we are forming different chemical species. So, you know, again, to make this even better of a model, what you can do to dive even deeper is to really figure out how can you determine the overall heat capacity of your particular wort if you are able to successfully determine the types of species that you have present. Because, you know, basically what's going on in here is you've got sugar, and you know, you can have side reactions present. You know, your hops or whatever can be undergoing some kind of decomposition. So figuring out like what is a good approximation of your specific heat capacity of your actual wort and of your actual coolant will help improve the accuracy of your model. So again, good things to call out here. But now what we'll do is we'll actually jump into MATLAB or Python, and I'm going to share that code with you guys. And then we're going to basically figure out, you know, how long should it take us if we make some assumptions on like what is our inlet coolant temperature, and, you know, we know our starting temperature of our wort. and we also know our flow rates and the types of materials that we're working with and the flow regimes, then we should be able to determine this time value. So, you know, I'm sorry, not sorry that this is as complicated as it is to just determine how long it should take to cool down a wort, but this is part of the reason why I think getting to make beer is so much fun from an engineering perspective. All the thermodynamics and physics involved here is really cool to actually get to see it in real life. So I'm going to now cut to that scene and stay tuned.